Any questions?
Yes, I have a question.
Yes, please.
Yesterday we said that U1 symmetry is not broken.
You mean the U1 Higgs case? Sorry.
I think we was talking about U1 electromagnetism. I mean, when we consider SU2, like when we move
U1 electromagnetism is for you and me is a good symmetry.
Yes, but we also.
Yes, sorry.
So my question is, we said U1 chiral symmetry is broken and U1 vector. Is that right? It's not broken.
That was a U1 chiral symmetry was not. It was just an example. Remember, it was nothing to do with nothing. I was teaching the principle of the Higgs mechanism, so I took some U1 chiral symmetry. It's not the real world in which we live, you and I. We live in the world in which there is a standard model symmetry, and we started discussing it yesterday. The SU2, we have to break SU2, learn, and so on. But first, before I go on, let me just say, it could be broken, U1 electromagnetic. Who knows? But seems not. If it is broken, if sometimes someone tells you that photon has a mass or the charge is not conserved, you and I will change that. Seems good. Okay, so this is the answer in the first part. Sorry, so now you are saying U1 chiral. Yeah, that was broken in our example. But it was an example. Is that what you're asking me?
Yes, I mean, like we said also U1 vector is not broken, and yesterday you said U1 is not broken. I mean,
well, some symmetries are broken, some are not. So I'm not sure what you're asking me. That's life. I'm sort of kidding. Remember, in the chiral symmetry, phi goes like this, and Q phi is phi. You agree? In my U1 chiral example.
Yeah.
The scalar field had a charge. So when Q acts on vacuum, you don't get zero. In other words, vacuum carries charge. Vacuum should be empty if the symmetry is good. So in other words, when I act with U on the vacuum, which is e to the I alpha q phi 0, this is not phi 0. I'm getting some new vacuum. We had a vacuum manifold, actually. I get a vacuum manifold, which was a circle S1. It was not a trivial point, okay? And so this is manifestly a case where the symmetry is broken, and you remember what we got? We got that the mass of the gauge boson is non-zero. It's not like photon. Agree?
Yes.
Okay, I have to ask you question by question. In our example, we also had, that I will not now write everything, a U1 vector symmetry, what I called, which was like this. Fermion was transforming. Well, let's call this beta, which meant that psi L and R transform the same way. Agree?
Yes.
This is why I call it vector. I call it vector because the current that is conserved looks like this. It's a vector current. Eminator teaches me. It's vector current, and let me just be even more clear. It's left-right symmetric. This is just Dirac algebra. The story. Okay, this is it. And remember, however, phi was invariant under this symmetry. In other words, Q, call it Q vector. This was some chiral charge. I don't know what name to give it. This is not our electromagnetic charge. This was some example. Let me call it some funny chiral charge. Higgs cavity field, Q vector acting on phi is 0. In other words, phi is invariant. But that means also that Q vector acting on phi 0 is 0. This is very important. No breaking here. Notice this funny charge, whatever it is, well, it's not so funny, it's a fermion number, is not broken because vacuum carries no such charge. Or if you wish, U vector acting on phi 0 keeps it invariant. Again, no symmetry, no spontaneous symmetry breaking of U1 vector symmetry. This is very important. We shouldn't be surprised. You know, the scalar field I'm taking, I didn't take color. For example, color will not be broken. This is why I chose the scalar field. Because otherwise you ask me, oh, but you are breaking Lorentz symmetry. No, I'm not, because this guy is invariant under. The only symmetries that are broken are those under which your field transforms, so that vacuum carries that charge. That will never be all the symmetries in the world. And this is, remember why I said I don't want to take a fermion field as an example. I could, but then I will break Lorentz symmetry. I don't want that. If I take a fermion field, if I do take a fermion field, imagine that I take a fermion field. So let's push this a little bit, since you're asking. So I take a fermion field. Can I have a combination that can get a wave? Remember, the problem is I don't want this. Is no good. Bad. Why? Because it will break Lorentz symmetry, for sure. Psi transforms under rotations and under boost, okay? That's not good. Okay, Lorentz, for you and me, is a good symmetry. We don't want to break it. Not today, not this month, not in April. Not, I would do the last thing in my life I would do is break Lorentz symmetry. Unless, of course, you tell me, well, experiment tells you that it's broken, then I will cry and see what to do, because my relativistic field theory is Lorentz invariant. But what could happen, however, is there a combination? So I have a question. Is there a combination that could get a wave? There is some noise. Is there a combination that could get a wave? Someone wants to help me here? Which conserves, so that it conserves, preserves Lorentz? The answer is yes. This, for example, this can have a wave. Psi bar psi is Lorentz invariant, as you know. That's why I write this. So in other words, it is possible psi bar psi could have a wave. Is allowed. But then I need to know some dynamics that creates such a funny bound state that gets a wave. By the way, there is an example in nature. This is just en passant. I may mention it again. The quark, anti-quark combination actually has a non-vanishing vacuum excitation value. This is produced by QCD. What is the dimension of Q bar Q? Who can help me? Fields carry dimension, you knew that. You actually told me that you knew what the dimension of a fermion field was.
Fermion fields carry dimension 3/2.
So what is the dimension of this?
So it's 3.
Thank you. So I can call it lambda. I don't know how to call it. You know, let's give it a name, lambda QCD. It's coming from QCD. Actually, it's something else, lambda QCD, but it's similar. Cube. Where lambda QCD is roughly, it's a little smaller, but imagine of order GV. When I say GV, it can be smaller. So actually there is symmetry breaking even without the field. In other words, W boson will get a mass, which is on the order of GV, but this is not enough. Actually, it's smaller. W is very heavy. So this is just en passant. We'll come back to this. Such things are possible. This was a great idea of Nambu that I will tell you towards the end of the course in 1960. He conjectured that Q bar Q could have a wave. Mass is this doesn't suffice to explain the gauge boson masses like WZ. We will break SU2. So in other words, and as usual, some symmetry will be broken. For example, Q bar Q. Now, just to explain to you, so Q bar Q is Lorentz invariant. So when I write Q bar Q, let me remind you that this is actually QL bar QR plus QR bar. Remember, it's like the mass term. So this, of course, is an SU2L doublet. By Q, I mean the up and down quark, just to be clear. So that QL is like this, and then there is UR and DR, they are singlets. So you see, so some symmetries can get broken. You write whatever you imagine. You should play with things, you know, write the things that will get away and then try to see what symmetries will be broken. So look what is nice here. SU2L gets broken, but it's okay, that symmetry is broken. W boson is Z boson is very different from the photon. There is no symmetry between them. You know that. So Lorentz symmetry is okay here. So for example, let's check them. Lorentz is okay. For example, SU3 color. Okay, because you have Q bar Q. If Q carries color, so it transforms. I don't write this color index like this. I don't have to worry about that because Q bar will go into Q bar. You see dagger. So therefore Q bar Q goes into Q bar. I hope you're following me. You see dagger, please ask me. You see Q, and this is invariant. So this also checks. I don't like to break SU3 color. I'm told that this is a good symmetry, so I can live with that. Okay, this is good. So you think of some symmetry that you have in mind. Electric charge. What about U1 electromagnetic? Well, QL is equal to QR. So again, this is neutral. So this checks. Again, another symmetry unbroken. Very good. And as you tell, is broken, and so on and so forth. This is how we reason. And this is from now on, I will always take a scalar field or a combination which is scalar, like Q bar Q. This is a scalar, really. Q bar Q is a scalar. This is a scalar. When I say scalar, I mean Lorentz, and so on and so forth. Did I answer your question in the beginning?
Yes, thank you very much.
Feel free to go on. I may not answer what you ask. So, you know, I'm giving you a flavor of, and this is why your questions will help. Remember, your questions is not just for you, they help your peers. You help each other with questions. You have similar questions. You have very similar questions which you do not ask. You can bet on that. What else do I want to say here? Now that you ask me before I go on, in our example, was there anything else? No, I guess that was it. We have two U1 symmetries. So, you know, when we write our physical examples, I won't always mention all the symmetries. I will try to remember and come back. So for example, when I do the standard model, ask yourselves, even before I tell you, oh, is there another symmetry that he forgot to mention here? Or maybe didn't want to mention now, but he will come in a week or so. The symmetry is not what you write. You say, I have a theory with this symmetry. Once you write down your Lagrangian, you may have much more symmetry than you know. And I often, when I referee papers or we read them, you find the wrong papers in which the authors do not really check the symmetry. They imagine that what they proclaim is a symmetry. So we got to be very careful, okay? When we suggest new models, new Lagrangians. Okay, very good. So let's go back, if you have no questions, to what we started yesterday. Let's do the symmetry breaking. I asked you to have a look to sort of be ready for today. I hope you did. And that was the SU2 Higgs mechanism, Higgs theory. It was very simple, remember? It was almost like U1. The Lagrangian, the Higgs Lagrangian of SU2 was particularly simple, was, let's put a half, because I wrote a half. Some books don't go to half, but then you normalize the fields differently. That's just a convention. So I have a covariant derivative, kinetic energy squared. I have a potential. This is as simple as this can be. This is my scalar field. And then I have generalization of Maxwell, which is Young and Mills. Which was what? Which was F mu A. F mu A. I don't even care what these F mu A's are. I'm not going to study them today. I just have to remember that gauge fields have kinetic energy. The crucial thing was phi. I have to define what phi is. That's U phi, which is e to the I ta theta a phi. This is where what we wrote yesterday. Ta tb is I epsilon ABC TC, and A is 1, 2, 3 ABC. This is the SU2 symmetry, non-trivial. This is what we call a doublet. Phi is a doublet. Not yet, I'm sorry. Now I'm going to define the doublet with Ta is sigma A over T. If phi was a triplet, it would have a different generators, okay, to talk about. It could be a quintet, it could be anything you want, but then the generators would not be 2 times 2 matrices. If it's a quintet, it will be 5 times 5 matrices and so on. Is this all I have to know? No, I have to also know that d mu is d mu minus Ig. This is the coupling constant of SU2. These are the generators. I wrote them above, A mu A. Remember, A can be lower or upper index, it makes no difference. The repeated index is summed. We decided it already before, like in the equation 1. So let's enumerate these equations. This is very important. The algebra, by the way, I talk of a group, but for me, really, the crucial thing is this algebra. Algebra and the group are not the same thing, but I sometimes will be careless. If we use the name group when I really mean the algebra. You guys know that SO3 and SU2 have same algebras, but they are not the same group. SU2 has a two-dimensional representation, spin half. SO3 only starting would be spin 1. And big. Okay. What else do we have to know? Okay, we have to know, this is very crucial, we have to know the potential, which we wrote exactly the same way as in the U1 Higgs case. This is my mass scale. All comes from here. This is the sign that guarantees spontaneous symmetry breaking. And remember, we said there are other terms that could be even others, but they will always vanish or will be equal to this one. For example, this is also invariant, phi transpose, I sigma 2 phi. Please, you must know this in your sleep. You don't need to take phi dagger phi, you can just anti-symmetrize. This is the famous anti-symmetrization. So this gives you spin. When I say spin, I mean the SU2 spin, of course, not the Lorentz spin. 0. But this is 0. It's invariant, but it's 0. So this is why the potential is so simple. What is the vacuum manifold? Vacuum manifold is set of all points phi 0. So that obviously phi 0 dagger phi 0 is V squared. Anybody has a guess what this manifold is? Now I'm talking about the group. I won't always worry about the group, that's not so important. More about algebra. Any guesses?
Is it an S3?
Very good. Very good, thank you. This is S3. Why is it S3? Just to remind you, I can write phi. There are many ways I can write phi, we will decide later. For example, the most logical would be phi up or phi down. I could write just up and down, but then you may think I'm talking about the quarks. Not necessarily, these are up and down components, but these are complex fields. Each field is complex. So I can also write like this, R1 plus I R2, R3 plus I R4, where Ri are real numbers. And then obviously phi dagger phi is sum 1 to 4 Ri square. So also the vacuum value would be like this, the vacuum value. And this, of course, is equal to V square. This is called the three-dimensional sphere. This is by definition S3, the three-dimensional. You can write it any which way you want. In general, you would write that phi 0 is something like this, which can be even complex number. Oh, why am I writing this? I'm sorry. It's just a doublet for U1, V2, which can be complex number, so that V1 squared plus V2 squared obviously is V squared. V was real. My Lagrangian is real, so V is a real number. Okay, but I will often take, you can rotate it any which way. You remember, if you have a vector you can rotate in one direction. I can also rotate phi 0 in one direction by SU2, just the way it's choosing a direction. I can also write like this. Let's call it phi 0 Goran. You can say, I don't like that. I don't know who wants to say. So we have phi 0, someone, other. Oh, I don't like that. I want to write like this. Am I going to be in trouble? Or someone says, I will write the one. Physics must be independent of the form of phi 0. Because there is a symmetry. I can pick up any point on this S3. They should be equal. This is very important. They should all give. Why? Because phi 0 Goran is some u, I don't know which one, phi 0 other, which is some u prime of that original one I took, y1, y2, and so on. Okay, you can find these u's, and of course this is just a rotation in the symmetry group space, and the way we formulate the theory, the physics should be the same. Let's convince ourselves. So let's see immediately let's do this. Let's study the main consequence. And that is the following: 1/2 d mu phi. Let me write like this. You know what I mean? This is the above term, goes into 1/2 d mu phi 0 square in the vacuum. And remember, the V is a constant, of course. Phi 0 is a constant. It's some V, combination of V, whatever it is, which means that d mu phi 0 is 0. So 1/2 d mu phi 0. Well, let's write, why don't I be more pedagogical, just to help you. D mu phi 0 then is minus I G TA A mu A phi 0. So 1/2 d mu phi 0 squared. The kinetic energy now in the vacuum is not 0. We see is 1/2 G squared. And then there is phi 0 dagger. I take first the TA A mu A. Remember, T is a Hermitian, of course. And then TB A mu B phi 0. The first piece comes from the dagger. The first schemes comes from one which had a dagger, of course. You're following me? This is 1/2 G squared phi 0 dagger TA TB phi 0. You see, I didn't have to specify for the moment. I can just go on. A mu A A mu B, which is 1/2 G square phi 0 dagger sigma A over 2 sigma B over 2 phi 0 A mu A mu B, which is equal 1/2 times 1/4 G square phi 0 dagger. Now, what is the product of sigma A, sigma B? It's delta AB. Who remembers?
Plus I epsilon.
Thank you. Epsilon A, B, C.
Delta C.
Sigma C, right?
Sigma C, yes.
Thank you. Phi 0. Very good. This is the piece inside times A mu A, A mu B. But notice that this is symmetric. In A and B. So the second piece goes to 0. Because it's anti-symmetric. Does not contribute. So what we got? That 1/2 d mu phi 0 dagger. Let's write now what we meant really now. Not to be symbolic anymore. Is 1/2 times 1/4 G square phi 0 dagger phi 0 A mu A which is 1/2 by definition m square A mu A mu A. In other words, all three gauge bosons got a mass MA, and it's equal. It's 1/4. Okay, let me write square. 1/4 G square phi 0 dagger phi 0. Notice I proved it doesn't depend on the form of phi 0. This is just an example. I will not do it every time. I will often choose my vacuum because it may be easier to do some calculation in some vacuum. You choose whatever you like. You don't have to follow me. But I guarantee you, which is obvious, that's group theory, you will get the one and the same result. So this is 1/2, no, 1/4 G square times V square. In other words, MA up to a factor half, which is just the way you normalize your generator. It's what we expected. We didn't expect them to be the same. This is surprising. The same mass. That was not obvious at all. We'll talk about it. We'll even, be perplexed about it. I broke the symmetry. Normally, when you break the symmetry, you don't expect the same masses. But before I discuss this interesting situation, we'll do some other examples in which the masses will not be the same. So, or at least one more example. So let's just leave it at this. Is what you expected. If they get a mass, this was the mass scale. And this is, of course, the interaction coupling. So if you get a mass, you know that the mass will be of the order of G times V. Then there is a normalization. This is an example. We say like this. All three gauge bosons got the mass that SU2 got broken to nothing, to identity, no symmetry anymore, through the phi 0 vacuum expectation value. SU2 gets broken completely to no symmetry, to nothing. We often write like this, just not to be surprised. Remember, the vacuum expectation value is just a notation. And why did it happen? It happened because TA acting on phi 0 was not 0. TA acting on phi 0 had to be non-zero for them to get a mass which is non-zero, which is, of course, which is equivalent to say that sigma A acting on phi 0 is non-zero. This is obvious. No Pauli matrix. This is how I got it. Okay, this is an equivalent stated. Okay, all generators are broken. All TA are broken. By the way, it may happen, it may not happen. There may be an example when half are broken or whatever. There was no a priori reason to break everything, but we will welcome it. All three are broken. Being broken, remember what being broken TA, when you have a generator TA, is equivalent to the statement that TA acting on phi 0 is non-zero. Because why? Then phi 0 carries, we call it charge. I mean, you know, it's just a generalization of electromagnetic charge, where the charge is the generator. We call it charge TA. And remember what we concluded, we were guessing this, okay? This is what the Higgs mechanism is. This is called the Higgs mechanism. Says, if you have a broken generator, Ti, let's call it some I, you will have a massive gauge boson, where you had in the covariant derivative, you have that particular Ti, A mu I, and I may be any number, okay? I is whatever, I don't know what I is, I have to do by inspection. I have to check whether my generators annihilate the vacuum. If they do not annihilate the vacuum, if they are broken, I will get a massive gauge boson. I'm not gonna prove the theorem. I will show you to you in the examples. But you can see from the example, we are actually proving it trivially, because when the generator acting here on phi 0 here is non-zero, then of course there will be a non-zero term which will be associated with the gauge field, and that will be the mass term because it's quadratic. You can see from the way we are writing that we are actually proving this generic theorem.
Professor?
Yes.
I'm actually confused because I think that what you have written, I mean, the last statement is actually Goldstone theorem. Because I thought that Higgs mechanism is you apply like a local gauge symmetry on Goldstone theorem. So maybe I'm wrong. I don't know.
Yeah,
I'm confused.
maybe you're wrong. There is, how can we speak of Goldstone here? This is a gauge theory. Notice that I've gauged it. I have a covariant derivative. Nothing to do with Nambu-Goldstone, with Goldstone theorem. So I'm not sure what you're asking me. Tell me what you thought. I'm discussing the Higgs mechanism. Higgs mechanism, remember there are two situations I've talked about separately. So Goldstone, which is actually Nambu-Goldstone boson, is a case of global symmetry. No gauge fields. It's very important. Whereas Higgs, which could be called Higgs and Glare, Brout, and so on, is the case sorry, I don't have to. Higgs case is the case of local gauge symmetry. I'm talking here about the Higgs. I've talked separately. I've told you in the case of Nambu-Goldstone bosons, there was no gauge field to talk about. There was a massless scalar field. I even showed you yesterday. We even show how one emerges from the other and so on. And there we have to speak. There we saw, in the U1 case, we noticed that a broken generator meant a massless scalar, which we may discuss even in the SU2 case, but I'm doing the Higgs now. Did I confuse you somewhere? That I wasn't
no,
clear?
no, yeah, I got it now. Okay. Actually, yeah,
sorry.
I was.
Okay.
We are on the same page actually. I just got
Look,
confused.
let's, I'm glad, please ask these questions, see how helpful it is, because there can always be a confusion. I know that you say things and I look how I'm repetitive, I tend to repeat things a lot in spite of repetition. Once again, it was manifestly a gauge Higgs theory. It's a gauge theory. I call it a Higgs theory. This is important. You could just call it SU2 gauge theory. Well, I call it a Higgs associated effect that I take an interesting potential. This is where the Higgs name comes. He didn't invent such potential. They were studied before by Nambu and Goldstone, especially Goldstone. He just applied it, he and other people, to the case of the gauge symmetry. So actually your question is really important because you could even told me, but you taught us first the Goldstone case. And that's maybe why you are still confused. No, I've changed the order on purpose. At the end, remember what I told you. There is no example of a Nambu-Goldstone in H. There could be, but there is not yet. Whereas Higgs is the standard model, therefore I've changed the order and I go directly to the Higgs. Now that I taught you, I gave you a mass and physics of the Higgs. So I will focus most of my attention on the Higgs. Not all, most. I will come back and comment on the Goldstone limit. It may even happen today. I'm not sure. Let's see with what speed we go. So what we are doing today is this. For the time being, let's forget this. And you can come and ask me what will happen. You can tell me. Don't forget to ask me if I don't ask you. Since you had this question, okay, you can come and say, but what happens if you take G equal to 0? If I take the coupling constant G equal to 0 here, I will get a Goldstone boson, a Goldstone case, because then the derivative is just the ordinary derivative. And that means that this Young-Mills field F mu nu A actually has nothing to do with the with us because it's decoupled. We'll come back to it. Is this clear completely? I convinced you that I broke the symmetry. This is very important to me, to all of you. I convinced you at least that I don't know what happened. I've convinced you here that we have broken. The question is now to study our field phi. Our field phi, I have just looked at the vacuum, but now what we have to study, what is phi? Inside phi, there were 4 components. Which field or fields are physical? They cannot be all physical, remember, because what happened is that I have these 3 gauge boson fields, AA. A is 1, 2, 3. All of them became massive. Which is 3 degrees of freedom. But we started with Young-Mills at the beginning, with Maxwell, with M0 before breaking. After break. That means from 2 to 3 component. In other words, we started with 2 component. And we ended up with 3 component. 3 of them. In other words, we got 3 extra degrees of freedom. Where do they come from? I can't get degrees of freedom, okay? They must come from the scalar field, right? Which means we said, these 8 guys eat someone. They were skinny, you know, they had no mass, as skinny as possible, and they got fat. So they had to eat someone. So let's see how to write. In order to do that, remember now it comes when I discuss phi, what variables to use. I keep emphasizing this. You know, what Weinberg tells you, make sure you choose the right variables. Otherwise you regret your choices. He did. Which variables? We must be smart now. How to choose the variables? Well, depends what we want to do. I told you that there is a very elegant way if you want to see the physics and not do the calculations, which was called unitary gauge. There is, after all, a freedom. So unitary picture, if you like, maybe. You choose the variables that you like. I can write phi like this, look. I could write it as, look what phi was. Let's go back and see what was phi. Obviously, you knew when you told me, when I was told that there is a 3-dimensional sphere, that actually there are 2 complex components. Each of them has 2 real components. So there are 4 fields. And I can write this as 2 complex numbers. Or I can write a complex number as real plus imaginary. But a complex number I can write also as the absolute value and the phase. So look at this way. This is sort of smart way. This is the way Weinberg wrote. E to the I, GI, TI. GI will be fields. So this must be over V to be dimensionless. 0, V plus H. Let me convince you that this is a perfectly legitimate choice. This is E to the I, GI, sigma I over V, 0, V plus H. This is, let's do the leading term, 1 plus I, GI over V sigma I, plus other terms. I just want to see what I'm doing to the leading order. For example, when I want to rid of kinetic energies or whatnot. The higher orders are interactions. So what will I get? I will get 0 V plus H, 1 plus I. I'm summing over I, okay? Please, when I have a repeated index, I mean the sum. So what will I get? Sigma 1, I know the form of, so why don't I don't need this I here, I'll put it inside with G. So for example, sigma 1, sigma 1 will give me a piece here,
Sorry, Professor.
or maybe a half.
Do we have the half in the exponential?
Thank you. Very good. Good, I anticipated you, right? It was sort of funny when you said sorry. We noticed almost, well, you noticed before me. By the way, there's just a normalization. You agree, I didn't have to do it like this. That's just a name for GI. If you don't like to have a G, this is choosing variables. You can choose them any which way you like. Make sure that then you normalize your mass term and kinetic energy, okay? We'll come back to that. Okay, so what will I get? IG1, you agree? 1 over V and V cancels. I'm looking at the leading term. You all with me? Plus IG2 times minus I from sigma 2. Everybody's following me? And then, oh, there is a half. Every time there is a half. There was a half. And then there is minus IG3 over 2. Plus, I've just written the leading term. Leading in fields. I don't take products. I don't take G times H, okay? That's a product, that's not leading, okay? Please, am I right? Are you checking on me? I'm just using the form of Pauli matrices, right? All I'm doing is to take that sigma 1 is 0, 1, 0. Sigma 2 is 0 minus I 0. And sigma 3 is diagonal here. That's why there is a minus sign, okay. So what I get is V plus H minus I G3 over 2, some funny normalization. No, not over V over 2. I didn't write smart. This 2 is sort of ugly. I shouldn't have written like this, but I did. Why do I want to write over V? Because I wrote before over 2. And then here I have G2 over 2 plus I G1 over 2. Notice that this is a perfectly well-defined doublet. I have 4 real fields. This is okay, this checks. Plus, so I had the right to write like this. This describes a complex doublet. Complex doublet has 4 fields. Now Weinberg says what we did in the U1 case. The next step is, if I choose that phi, I could also take a gauge variation, some U times phi is also good. Agree? Well, this is some local SU2. So in other words, U is e to the I, theta I of x, sigma I over 2. In a gauge theory, in the theory with the symmetry, any phi is as good as any other. And now I'm going to take theta I, but I take a particular theta I, which is minus gi over v. Gi is a function of x. Says Weinberg, this is my choice. Says Goran. Any is good, and phi goes into 0v plus h. This we often call phi unitary in the unitary picture. This is physical. The other guys here were not physical. If I can get rid of some degrees of freedom by gauge transformation, they're not physical. In other words, what I've learned, J-ions are not physical. They don't exist. They are a illusion, sorry. They are not physical. You may write them, but they can surely not exist. You cannot have these extra degrees of freedom. What happened is that AI eats GI, just like in the U1 example. This is equivalent to the statement. They become longitudinal components of GI. In the process of a gauge transformation, you have to, of course, change. When you do that, remember AI changes also. We showed this in the U1 example. I told you when we did U1, don't worry, guys, that it's U1. All the relevant physics will be there. The only difference will be some countings, some group theory numbers. In other words, I can work phi is this. This is often called a gauge. Actually, it's not a, I mean, strictly speaking, this is the physical, if you call it a gauge, a physical picture. And in the physical picture, there is only one guy. This is called the Higgs field. And this will turn out is precisely the situation in the standard model. Although there is a doublet, the example I'm taking is not yet standard model, but is very close. Because I'm breaking SU2, which really happens in the standard model, there will be some minor modification. The essence of symmetry breaking is in this example, okay. This you have to somehow follow. It cannot be simpler. We are lucky that out of this mess, there is only one physical field to look for. We'll write its interaction in a second. I'm just waiting to see if there is some confusion here, but maybe you want to ask me something. Okay, so you and I will, when we want to understand what is going on, we will always resort to this particular unitary picture. That's very important. Just to make sure that you're following me, I'll take a break I really don't need now. I'm in a mood to go on, but I think it's good to pause to be sure that I don't lose you. Let's meet back and what is it, 12:04? So the good time is say 12:10. Let's choose a round number. See if there was something that I rushed through. I will start sort of a bit studying the physics of the Higgs field. Okay. Should I go on? Any questions? Look, if this is the field which is physical, I can also check now what it means. Let me write the potential. It's phi dagger phi. And it is. I just rotate the fields. I use the gauge symmetry. This is V plus H square minus V square, everything square. There is a quartic term. There is a cubic term. This is interaction. Here, these two terms, plus a 1/2 mh square times h square. This is the mass term. And I know that mh square is 2 lambda v square. Remember, we always get one and the same result, which I promised to you. When there is a symmetry breaking, doesn't matter whether I take discrete case, whether I take a continuous case, which is Goldstone. The guy that lives around the vacuum expectation value that I call the Higgs field, which is maybe not completely fair. People noticed it before, especially Goldstone, that it clearly doesn't matter. It has a generic feature that the mass is proportional. Again, this is the scale. This had to happen because lambda is interaction. And keep this in mind. People often say that in this Higgs picture, the mass of the Higgs field is not predicted, that it's very ugly, okay? This is not correct. MH is actually, the number is not predicted, but it is related. It becomes dynamical to the interaction. That will be true of any particle in the world. Okay, interaction, notice lambda is a measure of interaction, which is lambda. So you have a dynamical property. You measure the Higgs mass, but also if you have enough of these particles, you will measure their interaction and you will find a profound correlation between the two. Look at the cubic term. It's the same V which enters and lambda. From these two interactions, in other words, so you have a mass term, okay, to be more clear even, mh square is 2 lambda v square. So you measure this independent. And by the way, in the standard model, you know, it was measured. This is not yet standard model, so let's be careful. And then you have interaction. So this is mass. And then you have interaction. You have two terms, lambda v h cube plus lambda, well, there was 4 h of the 4. If you measure both of them, notice you measure both lambda and v measured. So now m Higgs is predicted. When I say predicted, I didn't predict the number by some theoretic things. I mean predicted from interaction, from here. And that's what you can do with the mass. You don't really predict the mass. We'll discuss it in the standard model. You relate it to the interaction. Mass is your mass scale. How can I predict the mass? I had to put some mass scale in my potential when I started the whole business. When an hour and 10 minutes ago, whatever, 15 minutes ago, I started by introducing here a scale. Therefore, this thing that people say, oh, I do or I do not predict the mass, it's silly. There is a mass will be an input. What you want to is the correlation to create between the mass and dynamics, okay? So this we have a dynamical theory of mass. Here I disagree with most people. Even Weinberg himself often says and writes that the Higgs mass is not predicted, as if the W boson mass is predicted. I think this shows it's not a fair statement. Historically, you see what happened. We measure the Higgs mass, not yet in interaction. If I measure first lambda and V from the interactions, then I will predict the Higgs mass. And I told you a little more about gauge bosons and so on when we. So this is our Higgs example. What about the interaction with the gauge fields? Well, this is interaction with itself. Let's think of the gauge fields now. So let's think of the Higgs gauge part. It's all here in 1/2 in the kinetic energy. It's kind of kinetic energy. It's a generalized kinetic energy. It's all here. D mu phi is d mu minus IG dA A mu A phi. So d mu 0 V plus H is 0 d mu H. That will give me a kinetic energy minus IG sigma A over 2 A mu A 0 V plus H. What do I get here? 0 d mu H minus IG help me here that I don't make a mistake. I will have, what do I have? There is a 2. I take out. Sigma 1 is off diagonal and sigma 2. So I will have V plus H. A mu 1 minus I A mu 2. This is just from sigma 1, sigma 2. And then I have sigma 3. So what do I have here? V plus H minus A mu 3. I think this is correct. Are you checking on me? Don't trust me. Look, I can write like this. I think I can write more elegantly. There is this piece which I write separately. This will just give me a kinetic energy. I don't know why I'm writing it. This will give greater kinetic for H. But this piece is very important. Let me organize it a little more. Minus IG 1/2. V plus H goes out. And then I have A mu 1 minus I A mu 2. And I have minus A mu 3. So from here, when I have 1/2 d mu phi square, I will have 1/2 d mu H square. the pieces which are crucial, this one, and then 1/2 times 1/4 g square v plus h square a mu 1 square. It's obvious what happens. You will get a mu 1 square plus a mu 2 square plus a mu 3 square. I'm taking phi dagger times 5, and therefore I'll get what I expected. Previously, remember, the first piece is here. I can write 1/2, 1/4, g square, v square, 1 plus h over v square is the same thing. Of course, the first piece here gives me MAI is 1/2 GV. This is what we saw before. The first piece, but we also get from here, in other words, 1/2. So this is equal 1/2 MA square AI mu square, written symbolically. There is also another important piece, which is half goes away, MA square over V H AI mu AI mu. This is the Higgs interaction, which is from using this from here. You get a master 1/2 MA square, but that's already we write. I can write if you wish, just to be square. I goes from 1 to 3. We had the master, and then we had the interaction 1 over V from the above formula is 1/2. There will be G M AI H AI mu AI mu. Precisely as it happened in the U1 case. Notice, with some coefficient, Higgs couples to mass. He gives the mass to the gauge boson, and he couples precisely to the mass, which is the interaction coupling constant, of course, G, because it's gauge. To itself, Higgs couples with lambda. He gives itself a mass which is proportional to lambda, and then he couples to self proportional to lambda. To a gauge boson, Higgs gives a mass which is here, it's proportional to G, and then he couples to the same gauge boson proportional to G. This is where we are. Exactly as in the U1 case. We have a complete parallel. I promise to you that the physics I've captured in the U1 case will simply carry over to whatever theory you look at. If Higgs gives you a mass, it will couple to you proportional to your mass. We are now proving the theorem, if you wish. By doing example after example. Okay, what else do we want to say here? I could introduce the fermions. I discussed the fermions. I can also leave them to the standard model. I don't want to introduce the fermion towards the end of the lecture. So let me comment here. Let me think what else I have to say. Oh, of course. Of course, remember, this is what we call the, this was a unitary picture. All of this was the unitary picture. Unitary gauge. Once again, let's call it, if you wish, phi unitary, 0V plus H. So what we have in the unitary picture, we have the Higgs scalar plus 3 Procca fields. Procca, remember, are massive gauge fields. That's what we have. With the couplings that I gave you above. But that means that the propagators of AI are the same propagator that we always have. K square minus MA square. There are 3 of them equal. And then G mu nu minus K mu M AI square. We are in trouble. This is bad. Shouldn't cross it, it's there. I don't know, that was stupid on my part. So the unitary gauge is beautiful to understanding what is going on, but it's not good for calculations. Cannot compute loops. When I say compute, I mean loops. And in the one case, we said, well, don't do that, just write. You would write the following. You could do any which way you want to normalize, but I can write just like this. I can take the linear terms from above, but there were some factors of half, which are a little stupid. I can write G1 plus IG2. I can keep these G fields. They are not physical. They are eaten by A1, 2, 3. The advantage, of course, is that we can go, now we have a gauge freedom to arc psi gauge. And I'm not going to bug you that. We did it in the U1 case. This is like having 3 U1 cases, okay? For every field AI that gets a mass, there is a corresponding GI, you keep it, and then you will get the famous, you know, there will be, in other words, there will be arc psi gauge, which would be gauge fixing term you will add, which will be -1 over 2 psi I. Then there will be day mu, A mu I, plus M A I, you would write G for each field. You don't have to sum it. M A is the same GI square. So that there is no confusion, okay? That you put one in the same terms, and it just go as in the U1 case. We get, from here, we will get the D of the GI propagator is I. We did it, k squared minus psi ma squared. Or if you wish, it's MAI. You keep the index if you wish, but they are the same. And
Sorry,
then,
Professor. I think we have in the gauge fixing, we have psi in front of mass.
Oh, yes. This is very important. Otherwise, it wouldn't work. Thank you. And this is why this psi is crucial. This psi carries here. Thank you. Delta mu nu, very good. For AI fields, it will be this one that we wrote before was minus I, k squared minus MAI squared. Well, it's one and the same mass in this example. I'm just writing because they could be different. G mu nu plus I wrote psi minus 1 in the way I wrote k mu nu. It was something like this. You can check me. I believe this is correct. But this is just sort of a repetition of what I did before. I don't want to rewrite everything. This is, so in other words, loops do in arc psi gauge, as we call the renormalizable gauge. So I would call phi, we could call it phi renormalizable. You see, it's a choice of variables. And we have to be used to that. Sometimes it's nice to write a complex number as just C, or real, this is the analogy. I can write a complex number like this, or I can write it as like this. Or I can write it like this. I don't know. This is just choice of variables. And we have to master that. We have to sort of accept what the Koch taught us. These fields are not physical. I don't have to worry about them. Just like the longitudinal and time-like component of the photon, I keep repeating this, they are not physical, but they are great for doing calculations. Okay, I prefer to keep them when I compute things. When I think of the photon, I think of a massless, two helicity states guy. But okay, that I've said so many times, maybe I'm boring you. I hope I bore you. I was asked at some point, but what would happen in the Nambu-Goldstone picture? So let's finish on this. There is almost nothing to say. What happens if I go to Nambu-Goldstone limit? Nambu-Goldstone case, I could have taken the same doublet. Well, that would be G equals 0 from the Higgs. I can start with the Higgs, and that's just going to the Goldstone case. Now, for example, phi transforms as e to the I theta a. Again, the same thing, sigma a over 2 phi, but eta a is a constant. And my Higgs Lagrangian goes then into Nambu-Goldstone Lagrangian. Actually, Goldstone, maybe I should call it. I shouldn't be afraid. Goldstone studied this particular case. Goldstone Lagrangian would look 1/2 d mu now. I don't have to write the covariant derivative. D mu phi minus the same potential V of phi. Forget the Yang-Mills fields, they have decoupled. So what is the difference from before? Again, I have the same vacuum manifold is S3, is the set of all points phi 0 square, phi 0 dagger phi 0 equal V square, is the same potential as before. This is the same. I can again write, if I write phi as e to the I gi sigma I over 2 V 0 V plus H. I can write like that, but these are physical now. I can't gauge them away. There is no gauge freedom. But notice that phi dagger phi with this variable is v plus h squared. They disappear from the potential. Therefore, mgi is 0. Period. Goldstone theorem. I have 3 generators, I told you in the beginning, call it A or whatever, phi 0 is non-zero. Every time one generator is non-zero, there is a GAI field so that MGA is 0. And Nambu-Goldstone boson. So instead of having a massive gauge field, the limit is trivial. I could have started like that. But this is secondary to you and me. You and I don't have to worry about this. Maybe we won't. We just have to know that I can always go to that limit. And the thing to remember is the following. So the bottom line is in spontaneous symmetry breaking. So in a nutshell, let's see what happens in a nutshell. Here is my summary. When TA acting on phi 0 is 0, is non-zero, then there are 2 possibilities. A massive gauge field, massless scalar field 0 in the Nambu-Goldstone global symmetry case, or MA non-zero in the Higgs case. GA physical. Here, no GA. This is every time a generator. I'm sort of proving it. I'm cheating. I mean, it's not that I could give you a general proof, but I won't do that. It would take us time and we would not learn much. Is that I will do some other examples, at least one. I break the generator in the Higgs case. So this is the gauge theory. And this is the global symmetry here. This is the gauge case. In the global symmetry case, it's trivial. I write the same way, only now I'm not allowed to eliminate GI. I can also write linearly the way I wrote. You will get the same result. This is just a convenient way of proving that the GI is 0. It's not in the potential. Since it's not in the potential, it has a 0 mass. It will be in the kinetic energy, of course. Someone is talking, please. Hello. There is someone talking there. You should stop, please. You have to move to a microphone. Unless you want to ask me something.
Yes, I have a question, Professor.
Yes, please.
When we had the mass term of Higgs in the potential in this case, and also in the U1 case, we also had the term that if we consider the discrete symmetry, we have the same term. And can we argue that both the discrete and the U2 symmetries are simultaneously broken, spontaneously broken at the same time by this term?
Let's see if I understand correctly. So you're asking me in my SU2 example, the potential is lambda over 4, phi dagger phi minus v square, everything squared, correct? That's
Yes.
what you're asking me. You are saying that there is a discrete symmetry, phi goes to minus phi. Is that what you are saying?
Yeah, I'm asking in the with this term, with this potential,
There is a symmetry, right? There is a...
Yes, I'm asking, can we argue that with this term, we spontaneously broke both symmetries at the same time.
Right. Well, that's what I want to answer you, but this is what you're saying. Before I answer that, I have to be sure. You are saying there is also discrete symmetry.
Yes, yes.
There is SU2 gauge symmetry or global, doesn't matter. But there is also plus discrete symmetry, call it D, phi going into minus phi. This is discrete, that's what you're saying. Well, there is no extra discrete symmetry. This is a very nice point. Phi going to minus phi is actually SU2. I'm glad you asked, because U equal minus 1 is SU2 symmetry. Remember what SU2 is. U dagger U is 1. Determinant to U is 1. You agree that minus 1, I mean, how does it look? It fooled you. It looks like a discrete symmetry. It's actually a continuous symmetry. I mean, it's discrete, but I can get continuously there. Let me see. So U is minus 1, which is minus 1 as I called 1, 2. It's actually an SU2 symmetry. I can actually write it like this. I can write it as e to the I. How can I write it? Pi sigma 3. Am I right that this is equal? After all, what is e to the pi sigma 3? This is cosine pi plus I psi pi sigma 3. Right. This is minus 1. It checks. But this is equal e to the I 2 pi sigma 3 over 2, which is e to the I 2 pi T3. This is the thing that you know from quantum mechanics when you studied spin. Spinorial representations are funny. When you go around by 2 pi, you don't come back to the same point. You have to do it twice. You get halfway. So you see how I got it. I got this minus 1 once again. In other words, e to the I 2 pi T3 is equal minus 1. But what is this e to the I pi? This is simply a part of I have this symmetry. So this is just the final point of doing a continuous symmetry. This is very important. This you will see beautiful examples in the in theories beyond the standard model. There are beautiful examples of fundamental discrete symmetries, even like charge conjugation and so on. There is something which is called SO10 grand unified theory. Doesn't matter what it is, but you find inside that even a charge conjugation of Dirac could become a gauge symmetry, okay? So what can happen is the discrete symmetry. This is a generic feature that often happens, is a part of a global, which then you can make local, but the point is global continuous symmetry. You're right that they are simultaneously broken. It's just not a new symmetry. By the way, for those of you that may have heard this, and if you haven't heard about it, but you want to know, you can ask that. I was written, actually someone wants to know, somehow we didn't make, so next week we'll meet at least once or twice and discuss some of we accumulate certain things. On Monday, we'll meet. I send you an invitation because there is already one question I'm asked on the hierarchy problem. Neutrinos not directly related to what I'm teaching. You can ask me anything in the office hours. So I will, let me just tell you, when discrete symmetry gets spontaneously broken, discrete symmetry, okay, let me put it like this. I don't know if you heard of this. Side remark. Digression. I mean, the lecture is over anyway. Spontaneous symmetry breaking of discrete symmetries implies something which is called domain wall. I didn't talk about it, and I couldn't. I don't have time to talk about. Remember, in the discrete symmetry case, there were two vacuas. Phi 0 was 2 point plus or minus v. What happens is actually that you create, like in ferromagnets, physical objects that carry energy between these two vacua. This is called domain wall. When you have a genuine discrete symmetry that is not part of continuous, but if D belongs to a continuous, so there is a physical difference, then no domain wall. Domain walls go into subject of so-called topological defects that includes magnetic monopoles even. It's a beautiful subject that I wish there is time I could say a few words at the end of the course. But for those of you interested, you can come and ask me in the office hours what I mean by this. That was a very good question. I'm glad you asked. Did I answer it fully to your satisfaction?
Yes, thank you very much.
Okay. Anything else?
I have a question.
Yes.
So we found out that the phi field has the same. I mean, all the three has the same mass. And
Not the 5. You mean the
3?
gauge boson?
Yes.
You confused me. You said the 5 field. Gauge boson, you mean?
Yes.
Okay. Sorry. Yes.
So is that because the way we choose the gauge, or I mean
The way we choose. Sorry. You must.
yeah, is that the way we choose the gauge boson, or
We didn't choose any gauge boson. We made no choice. I'm not sure what you mean by choosing a what. Maybe maybe it's me not understanding. Sorry, what you are asking me.
yeah. So we found out that they have the same mass.
Yes, it took case.
Yes.
I wrote this. There's no choice here. I cannot write differently. This is the only way to get to the Young-Mills invariance. You have a generator and you have a gauge boson. The only thing I took one and the same coupling constant, but that of course is true. This must be same. This is dictated by SU2 symmetry. If I take different coupling constant JI, you wouldn't have the symmetry. So this is the most general covariant derivative. So nothing with the choice of gauge bosons, you agree? I cannot choose gauge bosons. That's the beauty of Young-Mills. Just look U1, right? Are you agreeing with me on this?
Yes.
Okay, now where the choice comes. So here, no choice. There is always some choice. The choice comes here. What I can choose is the Higgs field. I can choose anything I like. So I chose today a doublet. Oops. This is a doublet. And this gave me, I found out that all the masses are the same. I'm glad you're asking me. They're all the same, equal to 1/2 GeV. An extraordinary prediction. I can also choose a triplet. After all, the SU2 algebra, it's like SO3. So I can choose some triplet. Now it's a real scale, phi is complex. Now here I have a real scalar. So I could call it phi1, phi2, phi3, you agree? Phi I are real. This is a triplet representation. Phi goes into U phi, but now TA, I don't know who knows. Someone knows how they look? Actually, they look like this. We'll talk about that. You can remember it in different forms because you know Pauli matrices, there is a freedom in how you call them. This particular one, notice TA, TB. Please check it. If you don't know this, and you should, this is what it means knowing SU2. That means you don't really know the group theory, but you know some formalism. This you must choose. That, of course, the symmetry breaking now may be different. So there is an interesting question. What happens now? I would write the potential, not very imaginatively. I will write it, phi, always phi dagger, phi, no, there is no, I wrote it now as a field, phi dagger phi, but it's real. So it actually is lambda over 4, phi transpose phi minus v square, everything square. So you asked me the question actually that I may or may not have discussed, but I was gonna do it probably anyway. Since you asked, we will do that. I'm whetting your imagination. Try to think about it for Monday. Try to work out for yourself. So I have a question for you. Can you guess or compute? You can think physically, you can think, guess or compute MAI. Do you expect them to be the same or not? You have to give it a light. It's not trivial. I don't want you to answer now, but I want you to play with it on the if you're interested, okay, well, if you're not, I'll tell you on Monday what happens. We can do it together. But it will help you a lot that you try to anticipate without reading in the books. Remember what I did, just to give you a hint? If you're still with me, let me give you a hint. Let me help you. If you have time and desire to play. I chose in the case of doublet, I chose, okay, here, doublet, phi 0 in the doublet case. I chose like this, remember? Now, in the triplet case, what would be a natural choice? Who can tell me? Maybe you're all gone.
0, 0, V?
Yes. You know, a vector you can always choose in one to a component, okay? And now you have to figure out the gauge boson mass. I'm not gonna bug you with this. I mean, the lecture was anyway, you were asking me questions, okay? In order to do that, you have to be sure that you know that these are the generators are good. These are interesting. I think actually in my notes on the WDK, it's there. I'm showing that this is the so-called spin 1 corresponds to the doublet and so on. TA is minus I epsilon ij. Anyway, so the answer to your question is whether or not the masses are the same depends on the choice of the Higgs field. Not only that they may not be the same, they may not all become massive. Sometimes you break very little symmetry. There was another choice, which was very important, and the choice was in the potential, the minus sign. If I choose the plus sign, there will be no symmetry breaking, all of them to be massless, okay? So there are two choices. So I finished the answering. I know I took some time, okay? So the answer is on the question is, what does MA depend on? What is the choice? Answer on the choice of Higgs, B on the choice of V, because I can always write lambda over 4, some combination, phi dagger phi, whatever I mean by that, okay? I can always take plus or minus V squared. There are two choices, of course. Now, we don't take the plus sign, so that, but there was a choice here. Of course, you can tell me if it's positive and then the choice is trivial, all are massless, okay? So the interesting case for you, I finish here, my long answer to you, because this you asked a crucial, fundamental question is, how will I know what happens? And by the way, I usually don't know what happens until I make my choice and then go through the computation. Okay. Did I help?
Yes, thank you very much.
Any other question? Well, it got late, and I'm sure we are all hungry. At 1 o'clock. So if that's it, I can only wish you a nice weekend. See you on Monday.
Thank you.
You guys.